On December 24, 2024, while most of the world was wrapping presents and watching holiday movies, NASA did something that scientists once called physically impossible. A small spacecraft, roughly the size of a car, flew directly into the atmosphere of the Sun. Not near the Sun, not close to the Sun, into it. And it was moving at 430,000 miles per hour, making it the fastest human-made object in the history of our civilization. At that speed, it would take you from New York to Los Angeles in about 20 seconds. And as it disappeared behind the Sun, all communication went silent. The team at Mission Control had no way to know whether their spacecraft was still alive. They just had to wait. This is the story of how humanity literally touched a star, and what we found when we did. Most people assume the Sun is dangerous simply because it is hot. And sure, the surface burns at around 10,000 degrees F. That is already hotter than anything most people can even conceptualize. But here's the thing. The surface is not the dangerous part. The dangerous part is the corona. The corona is the Sun's outer atmosphere, a massive invisible envelope of plasma that extends millions of miles into space in every direction. And the corona is not just hot, it is shockingly, inexplicably, almost offensively, musing hot. While the Sun's surface sits at around 10,000 degrees F, the corona reaches temperatures between 1 and 3 million degrees F. That is up to 300 times hotter than the surface directly below it. Now, think about that for a second, because it fundamentally violates what we know about how heat works. If you stand next to a campfire, the further you walk away from it, the cooler music it gets. That is the most basic law of thermodynamics. Yet, the Sun does the exact opposite. As you move away from its surface and into the corona, the temperature skyrockets. Physicists have called this the coronal heating problem, GAD. And for more than 80 years, it was one of the greatest unsolved mysteries in all of astrophysics. But it is not just a scientific curiosity, because it is from this corona that the solar wind is born, a relentless stream of charged particles that blast outward from the Sun in every direction at speeds between 200 and 500 miles per second. That stream reaches Earth. It hits our magnetic field. And when it hits hard enough, it creates geomagnetic storms that can knock out satellites, GPS systems, disrupt radio communications, and overwhelm entire power grids. So, understanding the Sun is not just an academic exercise. It is about protecting the infrastructure that modern civilization runs on. Before we get to the mission itself, there is a story you need to hear, because the spacecraft is named after a person, and that almost never happens. In 1958, a young astrophysicist named Eugene Parker sat down and wrote a scientific paper arguing that the Sun constantly emits a stream of charged particles flowing outward through the entire solar system. He called it the solar wind. When he submitted the paper to a leading physics journal, the editor sent it back. The peer reviewer, a well-respected scientist, wrote that the paper contradicted established physics and should not be published. Parker appealed. The journal eventually published it only after the intervention of the editor-in-chief, Subrahmanyan Chandrasekhar, who would later win the Nobel Prize in Physics. 2 years later, spacecraft measurements confirmed that Parker was completely right. The solar wind existed exactly as he had described it. And over the following decades, Eugene Parker became one of the most important figures in solar science. So, when NASA was preparing to launch a mission directly into the Sun's atmosphere, they decided to do something they had never done before in the agency's entire history. They named the spacecraft after a living person. Parker was 91 years old at the time of the launch. He stood on the launch pad in Florida and watched his namesake rocket into the sky. He passed away in 2022 at the age of 94. having lived long enough to see his spacecraft transform our understanding of the star he spent his life studying. That detail matters because it tells you exactly how significant this mission was considered to be even before it launched. Here is the engineering problem that kept physicists and aerospace engineers awake at night for decades. How do you build a spacecraft that can function inside the atmosphere of a star? The sun-facing surface of the ParkerSolarProbe reaches temperatures of around 2,500 degrees Fahrenheit during close passes. That is hotter than lava. That is hot enough to melt steel, aluminum, titanium, and most other metals you can think of. And yet, the scientific instruments sitting just behind the heat shield operate at roughly 85 degrees Fahrenheit, essentially room temperature, through a piece of material that is only about 4 1/2 inches thick. The solution is one of the most elegant pieces of engineering NASA has ever produced. The heat shield, officially called the thermal protection system, is made of 2 panels of carbon-carbon composite sandwiching a core of carbon foam. That foam is 97% air. It is extraordinarily light and extraordinarily strong. And it is one of the most effective thermal insulators ever flown in space. The sun-facing side of the shield is also coated with a special white paint that reflects the majority of incoming sunlight, rather than absorbing it. But here is the part that surprises most people when they first hear it. The corona temperature is 1,000,000 degrees, and yet the spacecraft does not vaporize. Why? Because temperature and heat are not the same thing. Temperature describes how fast individual particles are moving. Heat describes how much energy those particles actually transfer when they collide with something. The corona is incredibly hot, but it is also almost a perfect vacuum. There are very few particles per cubic centimeter, so while each individual particle is moving with enormous energy, there are so few of them that the actual heat load delivered to the shield remains manageable. The spacecraft is not surviving by swimming through a 1,000,000-degree bath. It is surviving because a 1,000,000-degree near vacuum turns out to be something a well-designed carbon shield can handle. There is one more engineering challenge that almost no one talks about. At 430,000 miles per hour, the thermal forces trying to tear the spacecraft apart are immense. The engineers installed flexible joints that allow the frame to flex and bend in response to those forces rather than resisting them rigidly and breaking. The spacecraft was literally designed to bend, so it would not snap. ParkerSolarProbe launched in August 2018, but it did not fly directly toward the sun. It could not. The gravitational geometry of the solar system makes a direct approach essentially impossible. A spacecraft launched from Earth carries too much orbital velocity and would simply overshoot into a wider orbit rather than falling inward toward the sun. To solve this, NASA used a technique called a gravity assist, essentially using the gravitational pull of another planet as a slingshot to redirect and slow the spacecraft. And the planet they chose was Venus. Over 6 years, ParkerSolarProbe flew past Venus 7 times. Each flyby used Venus's gravity to bleed off orbital speed and pull the spacecraft's orbit tighter and tighter around the sun, like slowly reeling in a fishing line. With each orbit, the spacecraft reached a new record close approach, a new perihelion, before swinging back outward and then falling inward again, closer than before. During those 6 years of progressively tighter orbits, the spacecraft was already making discoveries. It found that the solar wind near the sun is far more complex and turbulent than anyone expected. It detected strange, zigzagging reversals in the sun's magnetic field, structures scientists nicknamed switchbacks, which appeared in far greater numbers than predicted, and which seemed to play a key role in accelerating solar particles to remarkable speeds. It flew through enormous coronal mass ejections, those massive explosions of solar plasma, and measured them from the inside for the first time in history. The final Venus flyby happened in November 2024. After that, there was nothing left to do but wait for Christmas Eve. On the morning of December 24, 2024, the team at Johns Hopkins Applied Physics Laboratory in Maryland was not celebrating the holiday. They were sitting at their consoles, watching telemetry data, and waiting for their spacecraft to disappear. As ParkerSolarProbe fell toward its closest approach, it entered a communications blackout zone, a region so close to the Sun that the intense electromagnetic radiation from the corona completely overwhelms any radio signal the spacecraft can transmit. The team knew this was coming. They had planned for it. But knowing something intellectually and experiencing it are very different things. At some point during that Christmas Eve, their spacecraft, a machine they had spent more than a decade designing, building, and nursing through 6 years of progressively closer orbits, went silent. Completely unreachable. No telemetry, no beacon, nothing. And there it was, 3.8 million miles from the surface of the Sun, moving at 430,000 miles per hour, flying on autopilot through the atmosphere of a star with no ability to receive new commands or transmit any data. For comparison, Mercury, the closest planet to the Sun, never gets within 28 million miles of the solar surface. ParkerSolarProbe was more than 7 times closer to the Sun than Mercury ever gets. On the evening of December 26th, 2 days after the closest approach, the Mission Operations Center received what they had been waiting for, a beacon tone. Just a simple radio signal indicating the spacecraft's health status. It said, essentially, "I am here. I am operational. Everything is working normally." The room reportedly erupted. Engineers who had spent years of their careers on this mission were openly emotional. When the full science data began downloading to Earth in early January 2025, researchers finally had something they had never had before: a detailed view of the Sun's corona from the inside. Not from a telescope pointed at it from a distance of millions of miles. From inside it, and the data immediately started answering questions that had been open for decades. The spacecraft's whisper camera, the wide-field imager for SolarProbe, captured footage of the solar wind being born. You could see the streams of plasma pulling away from the corona, accelerating outward, organizing themselves into the patterns that eventually reach Earth. Scientists describe this as something like finally being able to watch a river at its source after spending decades only ever observing it hundreds of miles downstream. Suddenly, the entire dynamics of how solar weather forms became visible in real time. The data also captured something that had only been predicted theoretically before. A phenomenon NASA scientists are calling the solar wind U-turn. When the Sun launches a coronal mass ejection, one of those enormous explosions of magnetized plasma, not all of the material escapes into space. Some of it loops back toward the Sun, pulled in by the Sun's own magnetic field, altering the corona and influencing the path of the next ejection. ParkerSolarProbe filmed this directly, up close, in detail no one had ever seen before. Understanding this feedback mechanism is critical for improving space weather forecasts, because it helps explain why some solar storms are far more powerful than others. And then there is the coronal heating mystery. The preliminary data from the close approach is pointing toward those switchbacks, those zigzagging magnetic reversals, as one of the primary mechanisms by which energy is transferred from the Sun's surface into the corona, heating it to millions of degrees. It is not one single process, but a complex interplay of magnetic reconnection events and turbulent wave activity. And Parker is giving scientists the resolution they need to finally map it properly. 80 years of mystery may be close to having an answer. ParkerSolarProbe has continued making close approaches throughout 2025, each time matching its record distance of 3.8 million miles from the solar surface and its record speed of 430,000 miles per hour. The Sun is currently near the peak of its 11-year activity cycle, which means solar storms are more frequent and more intense, and Parker is collecting data right in the middle of it. But step back for a moment and think about why this actually matters in practical terms. Right now, every time a major solar storm approaches Earth, satellite operators get somewhere between 15 minutes and a few hours of warning. That is barely enough time to put satellites into safe mode, let alone protect large power infrastructure. A sufficiently powerful storm, one comparable to the 1859 Carrington event, could trigger cascading failures in power grids across entire continents. Some estimates suggest recovery could take months or even years at a cost that would make almost any other natural disaster in history look minor. The data ParkerSolarProbe is gathering near the Sun, seeing how solar wind forms, how coronal mass ejections behave at their source, how magnetic structures evolve before they launch, is the foundation for building genuinely reliable, early warning systems. Instead of 15 minutes of warning, we could eventually be talking about days. That difference is not just scientifically interesting. It could protect trillions of dollars of infrastructure and millions of people who depend on it every single day. On December 24, 2024, a machine built by human hands flew into the atmosphere of a star. It survived temperatures that would vaporize any ordinary material. It moved faster than anything we have ever built. And it came back carrying data that is already rewriting textbooks. For thousands of years, every culture that looked up at the Sun treated it as something untouchable, a god, a mystery, a force beyond human reach. NASA just reached anyway, and what ParkerSolarProbe found inside the Sun is not just going to change how we do science. It is going to change how well we can protect the civilization we have spent so long building. If you found this video interesting, hitting the like button genuinely helps YouTube show it to more people who would appreciate it. And subscribe if you want to be here for the next music one. Because we are going to talk about what the James Webb Space Telescope found. Music at the edge of the observable universe. Something that, according to every model we had, simply should not exist.